We're starting to see the finish line of Physics GRE Gr0877. We're on problem number 61. A particle of mass m and charge q moving with a velocity v enters a region of uniform magnetic field B as shown in the figure above. The particle strikes the wall at a distance d from the entrance slit. If the particle's velocity stays the same but its charge to mass ratio is doubled, at what distance from the entrance slit will the particle strike the wall? So we're going to apply the fact that mv squared over r equals qvb. Where in this problem, v squared, the velocity, equals a constant, and b also, as the problem states, is constant, the magnetic field. So m over r is proportional to q, and 1 over r is proportional to q over m. So if the charge and mass ratio is doubled, then 2q over m is proportional to 2 over r. So m over 2q is proportional to r over 2, and r in this problem is the distance, so that is answer E. Number 62, consider the closed cylindrical Gaussian surface above. Suppose that the net charge enclosed within the surface is 1 times 10 to the negative 9 coulomb, and the electric flux out through the portion of the surface marked A is negative 100 Newton meters squared per coulomb. The flux through the rest of the surface is most nearly given by which of the following? So we're going to use Gauss's law that the total electric flux out of a closed surface is equal to the total charge enclosed divided by the electrical permittivity EO. So the total flux out of A is 10 to the negative 9 coulomb divided by EO, and that in the problem states is negative 100 Newton meters squared per coulomb. And we're going to remember that charge is held at the surface. So the total charge out through the rest of the surface is the total flux minus the flux out of A, and that's 100 Newton meters squared minus negative 100 Newton meters squared, and that equals 200 Newton meters squared. And we know that the total flux enclosed within this surface, as the problem states, is proportional to 1 times 10 to the negative 9 coulomb per EO, and so we get 200 Newton meters squared per coulomb, and that is answer E. 63. The nuclear decay above is an example of a process induced by the, and so in this case nitrogen N changed to carbon C, so the number of protons changed. Also a neutrino was created, and we can see that right here. That's our neutrino. Both of these are indicative of the weak nuclear force, and so that is answer D. 64. Consider a single electron atom with orbital angular momentum L equals the square root of 2h bar. Which of the following gives the possible values of a measurement of L subscript Z, the Z component of L? So we know that orbital angular momentum L equals, and it equals this formula right here. Lowercase l, you're just going to have to memorize it. Lowercase l times L plus 1 the square root of that times h bar. So L of Z equals mh bar. M is a magnetic quantum number. So the square root of 2 h bar equals lowercase l times the square root of L plus 1 h bar. 2 equals lowercase l squared plus l, and L equals 1. For a given L, there are quantity 2 lowercase l plus 1 values of m, from negative nh bar to ... for example, nh bar where n equals 0, up to positive nh bar where n equals 0, 1, 2, 3. And we have 2 lowercase l plus 1, and this problem equals 3. So the lowest 3 orbital angular momentum states are negative h bar, 0, and h bar. And so that would be answer D. And negative orbital angular momentum just means moving in the negative coordinate direction. Number 65. Characteristics of the quantum harmonic oscillator include which of the following? Number 1, a spectrum of evenly spaced energy states. Number 2, a potential energy function that is linear in the position coordinate. Number 3, a ground state that is characterized by zero kinetic energy. Number 4, a non-zero probability of finding the oscillator outside the classical turning points. So for 1, yes, n equals 0, 1, 2, so evenly spaced, and we can see over on this diagram provided by Hyperphysics, thank you. So evenly spaced. For number 2, no, it's proportional to x squared, not proportional to x. For number 3, no, the ground state is n equals 0, which is e equals 1/2 h bar omega, and that would be down here. And for number 4, yes, the wave function is continuous at the boundary. That is our quantum tunneling. So for number 65, the answer would be only number 1 and number 4, and that is C. Number 66, a muon can be considered to be a heavy electron with a mass m subscript u equals 207 m subscript e. Imagine replacing the electron in a hydrogen atom with a muon. What are the energy levels E subscript n for this new form of hydrogen in terms of the binding energy of ordinary hydrogen E subscript O, the mass of the proton m subscript p, and the principal quantum number n? So we know that the energy of our ordinary hydrogen atom is going to equal negative m subscript e, which is the mass of the electron, times e to the 4th, that's the fundamental charge of the electron, divided by n squared h bar squared 2 times the quantity 4 pi EO, that quantity squared. And so we're going to need to, because the mass of the muon is not negligible now in the hydrogen system that it's being put into, we're going to need to convert to the reduced mass. So the reduced mass of the electron system is right here, the reduced mass of the muon system is right here, and the reduced mass of the muon system is m subscript m, the mass of muon, times m subscript p, the mass of the proton, that quantity divided by m subscript m plus m subscript p. And then the same thing for the reduced mass of the electron above. So we know that the energy between the two systems are also proportional to the masses and also proportional to the reduced masses. So the energy of the muon system is divided by the energy of the electron system is proportional to the reduced mass of the muon system divided by the reduced mass of the electron system. So if we plug in our reduced mass of our muon system right here, m subscript m times m subscript p divided by m subscript m plus m subscript p, that divided by the reduced mass of the electron system, m subscript e times m subscript p, that quantity divided by m subscript e plus m subscript p. And if we do some algebra, we get our solution down here, which is answer D. 67. A large parallel plate capacitor consists of 2 square plates that measure 0.5 meters on each side. A charging current of 9 amps is applied to the capacitor. Which of the following gives the approximate rate of change of the electric field between the plates? So we know the electric field E equals Q divided by EOR squared. So dE dt equals 1 divided by EOR squared times dQ dt. dQ dt also equals I, the current. So the current I equals the integral of dQ dt equals Q divided by T. So dE dt equals I times the quantity of 1 divided by EOR squared. So dE dt equals 9 amps divided by EO times 0.5 meters squared equals 1 divided by 0.25 times 10 to the negative 12 meters seconds divided by volts, and that equals answer D. '68. The circuit shown in the figure above consists of 8 resistors, each with resistance R, and a battery with terminal voltage V and negligible internal resistance. What is the current flowing through the battery? So resistors in series, R total equals R1 plus R2 plus R3. Resistors in parallel, 1 over R total equals quantity 1 divided by R1 plus 1 divided by R2, that quantity, plus 1 divided by R3, that quantity, dot, dot, dot. So we're going to convert the circuit to a simpler circuit. So from this, we convert to here. I drew a very pretty picture. Hopefully you can see how we're converting it. Got to know batteries for the physics GRE. And then we're going to convert it again to a simpler circuit right here. And we can clearly see that I equals V over R equals 3V over 2R. And this circuit right here off to the side, when you have a circuit off to the side, that is not in the way of the current at all. So right here is our main, the main bread and butter of the problem. And so I equals 3V over 2R, and that is answer D, 69. In the AC circuit above, VI is the amplitude of the input voltage and VO is the amplitude of the output voltage. If the angular frequency W, omega, of the input voltage is varied, which of the following gives the ratio of V over VI equals G as a function of W? The impedance Z is the measure of opposition that a circuit presents to current when voltage is applied. It's similar to resistance. So the impedance of an ideal resistor Z equals R, but the impedance of a capacitor Z equals 1 over IWC, where C is a capacitance and is a constant, and the capacitor stores the charge. So V equals IR and V equals IZ, and I equals VI divided by Z. So you can walk through lots of steps down here. I encourage you to follow the steps through. If I read it, I would run this video into the ground talking about all the omegas and R's and C's. But so as W omega gets large, V over VI gets small, which is what answer D displays. So the answer is D, and again I encourage you to follow the algebraic steps. Number 70. A wire loop that encloses an area of 10 square centimeters has a resistance of 5 ohms. The loop is placed in a magnetic field of 0.5 Tesla with its plane perpendicular to the field. The loop is suddenly removed from the field. How much charge flows past a given point in the wire? So we're going to apply Faraday's law of induction, where the EMF equals negative N delta BA divided by delta T, and that's going to equal the voltage, where here N equals 1. It's the number of loops, and the magnetic field is constant, so V equals IR. I equals delta Q divided by delta T equals V divided by R. So delta Q equals the negative of B times the change in area divided by resistance, and the change in area equals area final minus area initial, and that just simply equals 0 minus 10 square centimeters, and that equals minus 0.001 meters squared. And so 10 times 1 centimeter times 1 centimeter equals 10 times 1 meter divided by 100 times 1 meter divided by 100, and the change in Q equals negative 0.5 T times negative 0.001 meters squared divided by 5 ohms, and the change in charge equals 10 times 10 to the negative 4 coulombs, and that is answer A. Okay, we're going to continue together, and we're very, very close to finish. I'll see you in the next set of videos.